Okay, so as the phrase indicate, all pass filter is all pass filter. So what do you mean by a low pass filter? You know that the frequency response of a low pass filter is something like this. Say if it is 0 to pi, let's have a cutoff frequency of omega c at 3 dB lower than the original value, and this is a low pass filter, and you know high pass filter has a response like this. And what do you mean by all pass filter? As the phrase indicates, it passes all the frequencies under consideration. So if it is from minus pi to pi, the whole range of 2 pi, it passes all the frequencies equally. It doesn't have any biasing or parity. So you may think, why do you need it? You may think that if you connect it through a wire, you get give xn, you get yn. So why do you need a all pass filter if this will do the job? So these all pass filters are usually designed when you need some delay or specific delay. If you use some all pass filter, you can precisely tell what will be the delay that you get. So when you want when you have some signals which comes in different phases, and if you want to have them synchronized, you can put enough number of all pass filters such that the overall delay is cancelled. So there are many applications. This is one of the application, and this is the use of all pass filter. So I know you may be wondering what is an all pass filter. Now let us see how to design an all pass filter. So as I have indicated, the frequency response h e raised j omega of or the magnitude E will be equal to 1, and it may have some phase. So you can represent it as e raised to j theta, where theta may also be a function of omega. So this is basically the magnitude response, or if you consider the whole transfer function, it will be h e raised to omega will be 1 into e raised to j theta function of omega. Now let us see how to design an all pass filter. So as indicated earlier, let us take say h z equal to 1 plus 3 z inverse by 3 plus z inverse. Can you try to find the transfer the magnitude response of this? Or should we use MATLAB for this? Okay, I'll take MATLAB. Otherwise, we can mathematically do it also. Probably I shall show it using MATLAB in next class. So we'll see what this is. H z is 1 plus 3 z inverse by 3 plus z inverse. Okay. First of all, what will be hz into hz inverse? What will be hz into hz inverse in this case? Let us find, or let us write hz inverse first. H Z inverse is 1 plus 3Z 1 plus 3Z. Instead of Z inverse, it will become Z 3 plus Z, right? So let us cross multiply this. So HZ into 1 plus 3Z inverse into 1 plus 3Z by 3 plus Z inverse into 3 plus Z. So if you cross multiply this, this become 1 plus, these two terms are multiplied, this become 9 plus 3Z inverse plus 3Z. So this you can write as 3 into Z plus Z inverse by denominator you have 9 plus 1 or 1 plus 9 plus 3Z inverse plus 3Z. 3 into Z plus Z inverse. So clearly you can see that this is 1. So these two terms cancels, numerator and denominator are same. So this is basically having a magnitude of 1 and it doesn't have any phase also. So its phase response is constant and its magnitude response is 1. So this is a 1 means it have a constant response over minus pi to pi, and hence this is an all pass filter. Now you would have noticed that Z is replaced by Z inverse. Suppose you take some general terms, say HZ equal to or before that HZ into Z inverse is 1 and hence this is an all pass filter. What have we noticed here? When I multiplied 1 plus 3Z by 3 plus Z, 1 plus 3Z inverse by 3 plus Z inverse with the HZ inverse, that is 1 plus 3Z by 3 plus Z, this became 3 into 3, 9. Okay. So here you have 1 plus 3Z inverse into 1 plus 3Z. Basically, when these, say, this term, the term that you have here is same as the coefficient that you have here. The term that you have here is same as the coefficient that you have here. And similarly, if you have all the terms like this, you can prove that this will be an all pass filter. So for example, let us take HZ equal to a more common A0 plus A1 Z raised to minus 1 plus A2 Z raised to minus 2 plus etc. up to say A m Z raised to minus m by say let us take this as am plus a minus 1 Z inverse plus etc. First term will be a0 Z raised to minus m. This term will be a1 Z raised to m minus 1 plus etc. So you can see that the terms that you have here, a0 is same as a0 here, a1 is same as a1 here, a2 will be here, similarly am will be here, am minus 1 that you have here will be here. So these are basically called mirror coefficients, and you have, suppose you have coefficients like this. Let us try to write this as, say, HZ equal to this is HZ equal to say sigma, or let us represent this polynomial as a some of order, a polynomial called dm of order m. So this can be written as dm set by how can you write this? Suppose you take z raised to minus some outside from this. Then what do you have inside? This is a0 plus a1 minus m you have taken outside. You have a0 a1 into z plus a2 into z square plus etc. Okay, so this is same as the z you take upside z raised to m dm z by what is down in what is this term a0 plus a1 z plus a2 z square plus etc. This is basically dm z inverse. Instead of z inverse, this z inverse have now become z. So that means z inverse or z is replaced by z inverse. So this can be written as dm z inverse. This is dm z inverse. Okay. So this can be written as z raised to m dm z by dm z inverse. Now, so you have written hz like this. Now, what we want to prove is this is having a magnitude of 1. Okay, or its magnitude response is 1. Now, let us find hz into hz inverse, hz into hz inverse, which is the magnitude response of hz. So hz square. To get the frequency response, we want to put z equal to e raised to j omega. So what will be hz into hz inverse? You just see this will be, this is hz. So what will be hz inverse? Again, change z to z inverse. So z raised to minus m dm z inverse by dm z. Now hz into hz inverse, how do you calculate? You multiply hz with hz inverse. So if you multiply these two, what you get is z raised to m dm z by dm z inverse multiplied by z raised to minus m, that is hz inverse. Hz inverse is this thing. So z raised to minus m multiplied by dm z inverse by dm z. So now you can see that this easily cancels out. This also cancels out. This also cancels out. Then this become 1. So the magnitude response is 1. So this is how, if you take coefficient of hz like this, that is a0, these two are same, a1 and are same, a2 are same. Similarly, this first term and last term are same. Second last and second terms are same. If you take like this is or you can very well represent the denominator as dm z inverse, and if you replace z with z inverse, you get an up in the numerator you again get dm z inverse, and if you cross multiply it cancels and it becomes 1, and hence it becomes a all pass filter. So any filters of this form is always an all pass filter. Now, depending on the order, you can get how many multipliers and adders are there. So depending on how many multipliers or adders are there, you can very well find what will be the delay in each all pass filter. So depending on that, you can design for a particular delay in each of these lengths. So this is how an all pass filter is designed, so let us find some all pass filters. Let's take HZ equal to say 1 plus Z inverse or 1 plus 2 Z inverse by 2 plus Z inverse. Absolutely, this is an all pass filter because 2 and these two are same. 1, 1, these are same. So this should be an all pass filter. And if you find HZ into HZ inverse, it will be equal to 1. So suppose that Z inverse, that is the delay by one element, or the unit delay, you call it unit delay. Unit delay depends on the sampling rate. So if you have sampling rate of say 8 kilohertz, which can be used for sampling speech signals, because speech has maximum 4 kilohertz. So Nyquist criteria for sampling it is 8 kilohertz. So if you have 8 kilohertz means between two samples you have 1 by 8000 second or 125 microsecond. So in between these samples you have 125 microsecond. So unit delay with a sampling rate of 8 kilohertz means it is 125 microsecond. So can you try to find what is the delay produced due to this all pass filter? You have an all pass filter, find the delay. You can try this as a homework, and probably I shall give some. Do you want to do it now or you will do it later? I want to get response from you. You can unmute and tell. I won't be able to see your chat. One of you can unmute and tell. Would you like to do it now or would I like to do it as homework? Am I able to? Are you hearing me? Am I conveying what I am supposed to? Can you answer? Yeah, okay. Now I can see the chats. But during presentation, I won't be able to see the chats also. So please unmute and tell when I'm giving presentation. Okay. So yeah, this is how an all pass filter is designed. Probably I shall give you some tutorials based on this. Yeah. So this is how an all pass filter is designed. So hope you understood. I think we can conclude today's class. If you have any doubt, please ask. See, as I have already told, the usefulness of these live classes is when interaction happens. So you can ask any doubts um, in the interactive session. Okay. Do you have any doubt? Okay. Then I think we can. Yeah. Yeah, I think this question was already asked. I got in the chat box. I got a question. What is the significance of it if all the signals are passed? Um, I think this I have already answered. The significance is that see when you have or when you require some delays, um, you can put a delay filter or you can put an all pass filter also. If you put a delay filter, it's not sure that all the frequencies are passed equally. But if you put an all pass filter, you can make sure that all the frequencies are passed through without any fluctuations. So when you have some analog signals that comes in, you can't put any delay flip flops and all because it's used for digital data. So when you have some analog signals coming in and you want to transfer it all together to the other end with a small delay, the delay can be precisely designed using an all pass filter. So when you have um, a precise all pass precise delayed all pass filter, you can design such that all the signals that are coming from various sides are reached synchronously, or whatever the purpose is, you can um, design particular delay for each of these signals that are coming in. So that's the usefulness of an all pass filter. All the I started with this, basically the class started with why do you need an all pass filter. Okay, I think that clears your doubt. Okay, Malvi, is there any further doubts? Okay, if there's nothing else, we can wrap around today's class. Thank you all of you. We can move to the next class.